Hi to you, and thanks a lot to listening to this tutorial on descriptive statistic, which aims is to give you basic notion in order to help you understand descriptive statistic. In this tutorial, we will show you how to use mean, standard deviation, median, mode, and as well as graphic in order to analyze your data. So the question that you are asking yourself right now can be, what is descriptive statistics? So the answer that I can give to you right now be simple is that descriptive statistics are brief descriptive coefficient that summarize a given data set, which can be either a representation of entire or a sample of a population. You also need to know that it can be broken down into measure of central tendency and measure of volatility that is related to the spread of your sample. So measure of central tendency include the means, median, and mode, while measure of volatility include the standard deviation, variance, the minimum and maximum variable, and the kurtosis and skewness of the sample. So descriptive statistic is used in different manner. First, to summarize and describe your data graphically or numerically, and to identify important characteristics as well as sharing information about your data. So what in which situation can be used, can be conducing descriptive statistic in the measure of time. Descriptive statistics are used in the conducing of statistic or scientific project. So you need to make to research your topic, make a hypothesis, write down your procedure, control sample variable, assemble your material, conduct the experience, repeat your experience, and now finally you need when you need to analyze your data and draw your conclusion, it is important to make descriptive statistic that can help you draw a conclusion. But sometimes you can need to go much further in your study, as well as making inferential statistic that is but in this tutorial we will only focus on analyzing your result using descriptive statistics. So in scientific project generally, you need to collect your data, presenting it, and make finally descriptive statistics. And to make descriptive statistics, you need to have basics on probabilities theory, probability distributions. You need to, if you want to go much further than descriptive statistic, and make an inferential statistic, you need to know how to estimate parameter. You need to have notion on confidence interval, limits, significance. You need to know how to make hypothesis testing. But for now, we just focus on descriptive statistic that got no further than using graphic, using mean and coefficient in order to analyze your data. So the outline of this tutorial video is use graphic technique as bar graph, line graph, scatter plot, relative frequency histogram, the pie chart, as well as numerical techniques such as measure for central tendency, volatility, relative standing, and box plot, that is a particular descriptive statistic tool that is at the same time graphical and numerical. So we start with the example of bioinformatics trend since 1992, that in which we show you the number of universities that are offering bioinformatics training program as in since the year 1997 to the year 2004. So you can see the different figure related to bioinformatics trend in such a university. So that's the data that are given at the right of your screen. For each year, you have the figure representing the number of university offering training in bioinformatics. So the first way to analyze and to represent such kind of data can be a bar graph. A bar graph can be used to show amount or frequency in categories. So you have categorical data and you need to make a graph. You can use bar graph. In our example, the year will be on the x-axis, and the number of university offering bioinformatics program will be on y-axis. For each year, a bar rise to the number of school offering the programs. Instead of just viewing the number, we can instantly observe that there is an increasing trend in the number of schools that offer bioinformatics programs. So you can visualize your bar graph here, in which I told you I represent in x-axis here, and on y-axis we represent the number of university offering bioinformatics training, so that you can observe that the number of students of university offering bioinformatics program has drastically grown over the time. The other way of representing data is histogram. Histogram is a little bit different to bar graph, in a way that in bar graph you only need your data to be categorical. So in histogram you need your data to be categorical, nominal, and ordinal. So that's the particularity of way of using histogram. So you need to have categorical and the other condition is that your data need to be nominal and ordinal. So the graphic represents the histogram is so the graphic representation of frequency table. So you have frequency table and you display bar vertically or horizontally where the area is proportional to the frequency of the observations falling into the class. So I illustrate it with a sample of a person having not more than 300 Facebook friends, and I represent the number of Facebook friends of my sample after grouping a variable number, which is the number of friends by class. The first class is 0 to 50 friends on Facebook. The second class is 51 to 100 person, and so on, as you can see on the graph. And the histogram represents the frequency, so that the area of every band is proportional to the frequency of the frequency of any class. Is most useful when dealing with large data set to show outlier and gaps in the data sets. That's histogram. So another way of representing data is line graph. Line graph is a good way to display the change in your data over time. The time interval or category are on one axis, and the data to be plotted are on the other. In our example, the year, our first example of bioinformatic courses, the year is on x-axis and the number of universities offering bioinformatics programs is on the y-axis. And for each year, a point is plotted at the corresponding height. Then the points are connected with line. Against we can instantly observe that there is an increasing trend in the number of schools that offer bioinformatics program, as you can see in this line graph materialized in your screen. You can see the evolution of the number of university offering bioinformatics program according to the year. So it's the growing trend of the number of university, as you can visualize right now. So we will take another example in order to illustrate other way of representation of data. But in this example, we will have a list of test score for 25 biology students, and out of 150 points, the students' score were recorded. We will look at the data in the scatter plot, a relative frequency histogram, and a pie chart. The numerical data is shown. So here is numerical data related to a classroom data, and the test score of 25 biology students are recorded, and the score is out of 150 points. So you can see the different score obtained by each of 25 biology students. The first thing I'm going to show you in this example is a scatter plot. It is simply a plot of all the test score, and for each student, number 1 to 25, place a point above the student number at his test score. This plot shows that the scores are distributed all over and that there isn't a lump of bad or good score. But other than that, this plot is uniformative. It's very uniformative. So let's look at something, the representation of scatter plot, in which for each student number 1 to 25, we just represent on y-axis his score, and you can see the scatter plot right now on your screen. So the other representation in this example that I just took right now is the pie chart. So from the table we created for our histogram, we can also make a pie chart or pie graph of the same sample. A pie chart is a circular graph that shows how a total quantity can be distributed among categories. So in our example, the category are the letter grade A, B, C, D, and F. I added a new column to our table to show the percent of the circle shared for each class. The area of each piece of the pie corresponds to the percent of test score in each class or category, and in this case for each letter grade. So you can see the representation of a pie chart. You can also look at classroom data score. We have different classes A, B, C, D, and E, F, and we have for any class a relative frequency, which is the frequency of the class divided by the total, the number of students that were recorded. So the area of any part of the pie chart is proportional to the relative frequency, and you can see the representation in the right of your screen. That's the pie chart. So the pie chart is suitable to represent categorical data used to show percentage, area are proportional to value to category, as I told you very soon. That's the case of Facebook film that I show you very earlier in this tutorial, and you can make a pie chart presentation of this situation. But be cautious, because you should never use pie chart to show historical data over time, and also you do not use for the data in the frequency distribution. So let's pass to the measure of central tendency. Central tendency is a summary statistic or a measure that describes the center of the distribution. The first measure of central tendency I'm going to show you right now is arithmetic mean, following by median and the mode. So arithmetic means, or simply the means, is equal to the sum of the measurement divided by the number of measurements. So mathematically, you can see at your screen how to compute a mean sample, a sample mean. So a sample mean is equal to the sum of observation divided by the total of observation. Population mean is calculated as you can see on your screen. But median is the value of the measurement that fall into middle position when the measurements are ordered from smallest to largest. So you search for the middle of the middle position when you classify your observation from the smallest to the largest. So I can show you a different method to compute median. The first case is the case where the number of measurements from smallest to largest is an odd number. While when you have the odd number, the median m is the value of the middle measurement, or the one rank n plus 1 divided by 2. If n is even, if you have an even number of observation, then the median m is the value halfway between the two middle measurements. It is the average of two middle values. But the mode is the category data that occur most often. And on the histogram, the mode is the class with the highest frequency. If there are more than one value in the class, then the midpoint for the class is the mode. So we can show the example in order to illustrate how to compute mean, mode, and median using the following data set: calculated mean, median, and mode. So we have a sequence of number 2, 3, 5, 5, 7, 7, 7, 8, 10. We will show you how to compute mean, mode, and median. So the data set is first of all rank from the smallest to the largest number. We have 9 observations. The mean is simply the sum of all observations divided by the number of observations, which is equal to 6. The median is the value that divided our sample into 2. So the number is the median. When we cross 7 divided our sample into two part. This equal into it divided our sample in 2, while after and before 7, the observation 7, we have the same number of observation, which is 4. So the median is 7. The mode is 7 because 7 have the highest frequency, which is 3. There is no other figure that appear more than 3 times as 7. So the mode is 7. So after a measure of central tendency, we can look at the measure of volatility, a summary statistic or measure that describe how the data vary or how it is dispersed. So we have range, we have variance, we have standard deviation to measure the volatilities. So the range of the set of measurement is a difference between the largest and the smallest measurements. So variance is a sample of a sample of data is a sum of square deviation. Square deviation is the difference between from mean, the difference from between every observation and the mean. And when we divided this sum by the number by n minus 1, you have the variance of your sample. So measure of volatility can be shown here. The variance of sample is a sum of difference to mean, the square difference to mean divided by n minus 1, and the standard or the standard deviation of the population is calculated as you see on your screen. So the standard deviation as last measure of volatility that we are going to show you here is just the positive square root of the variance. So you have your variance, you calculate the square root, and you have a standard deviation. It means the variation of the score about the means, which means the average deviation from the means. So that's a statistical interpretation of standard deviation, and the calculation is given at your screen at the square root of our standard deviation of our variance that we have just defined earlier. So an example in order to illustrate the calculation, we took the same example, a sequence of figure 2, 3, 5, 5, 7, 7, 7, 8, 10. We take this example in order to illustrate the calculation of dispersion tendency. So we have our data sets, we have the range, which is the difference between the highest and the lowest values of our sample, which is 10 minus 2, which is equal to 2. So the range of our sample is 2. The variance is, as I told you, the difference, the mean, the sum of square of difference to means divided by number of observation minus 1. So you can compute our standard variance and find out that it is 6.25, and the standard deviation is just the square root, the positive square root of our standard of our variance, which is 2.5. So another way in descriptive statistic is relative standings. Relative standing often is important to know how one data point relates to other. It is relative standing. We have sample z-score. Z-score is a measure of relative standing. And the sample z-score measure the distance between the observation and the mean, measure in unit of standard deviation. So you can see the calculation of z-score, which is difference between the observation and the mean divided by the standard deviation. As I told you, the z-score of the observation measure the distance between observation and the mean, measure in unit of standard deviation. So another relative standing is percentiles. So if you have n observation, x1, x2 to xn, and we have and we suppose that our measurements are arranged in order of magnitude. The pth percentile is the value of x that exceeds p% of the measurement and is less than the remaining p minus 100 minus p%. So that's the percentile of our sample. So another relative standing is a quartile. We have the lowest quartile is the first quartile, which is the 25th percentile. So the second quartile, also called the median, is the 15th percentile, and the upper quartile or the third quartile is the 75th percentile. So that's the definition of our different quartile, the first quartile, the second quartile, and the third quartile. That's defined as you can see on your screen. So the last thing that I'm going to show you is a box plot, which is explanatory data analysis. So explanatory data analysis is a process of using statistical tools such as graph, measures of central tendency and variation to investigate the data set in order to understand the importance characteristics good for seeing outlying observation. So what's outliers? Outliers is extreme value located very far away from most of the other values. They can have a drastic effect on the mean, standard deviation, and on a scale of the histogram, so that the true nature of the distribution is totally obscured. So box plot reveal the center of the data, spread of the data, distribution of the data, presence of outlier, excellent for comparing two or more data sets. So you can see at the right of your screen what box plot are represented, and we will show you very sooner how to make it possible. So to construct the box plot, you need 5 summary statistics. You need to have the mean, you need to have the first quartile, you need to have the median or the second quartile, you need to have the third quartile, and you need to have the maximum. So while you have the 5 summary statistics, you can plot your box plot. So to construct the box plot, you calculate the first quartile, median, and third quartile. Calculate the interquartile range by subtracting the first quartile from the third quartile. So construct the box above the number line bound on the left by the first quartile Q1 and on the right by the third quartile. So after that, you indicate where the median lie inside of the box with the line, dividing the box at the median value. The mean value of data can also be labeled with a point. So you have a rectangle in which you plot the median as median value. You have the first quartile, the third quartile also, and you can highlight also a mean, as you can see at the back of your screen. So any data observation which lie more than 1.5 interquartile difference lower than the first quartile, or 1.5 times higher than interquartile difference than the third quartile, is considered as an outlier. Indicate there the smallest value that is not an outlier is by connecting it to the box with the horizontal line. Also, mark the position of this value more clearly using a small vertical line. Likewise, connect the largest value that is not an outlier to the box with a horizontal line, and mark it with another small vertical line. Indicate outlier by dots. So you have one outlier, which is the value that is 1.5 times higher than interquartile interval. So that's it for this tutorial on descriptive statistics, and I hope it will help you understand many things on descriptive statistics, and I will see you very early in other tutorial related to this notion.